A very warm welcome from my side for this talk about Polyglot Architectures. My name is Stefan Kolmar. I'm leading the professional service and the pre-sales team at Neo4j. So as an agenda for the next 35 minutes, if I'm not mistaken, I have prepared the following content. First of all, talking about what are the drivers for change in enterprises these days. And these drivers for change, they create some requirements for polyglot architectures. So in other words, why do we need that, right? Then I will actually a little bit an overlap to what we just saw. We'll talk a little bit about traditional approaches, the benefits of using graph technology. Then I will introduce Neo4j as a native graph database, and then actually as kind of coming to the core of it, right? Discussing a couple of architectures and ecosystems using a graph database in conjunction basically with case studies, and then we conclude the talk. So what are the drivers for change in enterprises these days? So on one side, we need to see, and I think this is what this day is about, or these 2 days are about, is about a data explosion. Why is that, right? I think it is mainly driven by the usage, the pervasive usage of the internet. So all of us are constantly on the internet. All of us are using smartphones, are creating a lot of data. And in a sense, what this is about is not only that we are creating the data is exploding, it is also a need to have a much finer granularity of data than what we used to do. Because with the smartphone as an example, you know immediately who the user is, where he is, what the location is, what kind of device he's using, and so on and so on. And of course, we want to take advantage of that, right? Then what we also see is the trend of going in the Internet of Things world, right? Which means there are billions of devices out there which will need to be connected. Data will be created. Data will need to travel from devices to backends and so on and so on. And of course, then also the cloud computing. The trend for cloud computing is creating a massive change in enterprises, because with hybrid clouds, as an example, you need to combine your internal IT with external clouds, right? You need to secure the access to different infrastructure, and you need, of course, then also to provide open interfaces and open ways how these different components are talking with each other. All of that has in common that there is a need to use connected data. So in other words, the days of isolated data, of data islands, are kind of counted, right? Because in the end, what you want to do is you want to have a homogeneous overview of your data. You want to really see what is connected with what. We talk about the connected enterprise, where basically all of the data in your enterprise is connected, so that you have a 360-degree view of your customer, that the customer basically is not living only in a CRM system, but the customer also, of course, is creating support tickets as needed. The customer is basically also then subscribed to articles or to products. These products evolve, has an impact on what is on our roadmap, what is in our internal pipeline to be rolled out, and things like that, right? Then also the need of, as I just mentioned, of the connected things, the IoT, and then also knowledge network. I mean, we talk so much about and so much with customers who have a rich variety of patterns of knowledge in their enterprises. But the key here really is to combine this, right? So that everybody in the enterprise knows who actually knows in my company about something, right? I do not need to reinvent the wheel. I need to find out, hey, who is the one who knows something about it? What has he already done? How can I get access to the data? How can I talk with him? What can I do with him? So there's a need for a knowledge network within the companies, and not only that, it's also outside of the companies. So if we see the status quo, then basically what requirements are created then for polyglot architectures coming from that? I mean, of course, it is big data. It's about the ability to handle large scales of data volumes. As said, in IoT, we are talking billions of devices creating gazillions of data, right? It needs a high availability 24/7. The internet never sleeps, right? So there will always be somebody who needs to be on. There is a need to have open interfaces. As said, it is not only about an island of information, it is about the connection within these different islands, right? And to provide not a heterogeneous, but a homogeneous view of the data. Structured data to take advantage of connections, very important, because in the end, what you need to have is the data in a way so that you can not only have the connections, but you can use them, right? And you can provide these connections also then to your end users and to the different demands. Which comes then together with the ability to query connected data on demand, so that, I mean, a lot of companies are doing that already. They are providing connected data. They are basically populating then different aggregated views, as an example, on connected data, but they do that actually in a batch time fashion, so that after the batch is run, basically you have, as an example, materialize the different connections or different recommendations you could provide, but that is not the point. I mean, the point is really that you need to do these recommendations and you need to do the connections in a real-time fashion, and you need to materialize them whenever you need it, right? And then, of course, to have the flexibility to connect and query data with different schema. Coming back to the talk, I was part of the last talk with Elasticsearch. Very, very true, right? I mean, there is a need really to not to have a static schema defined at one point in time, but to have some flexibility and to provide the flexibility. So in the end, this is about using the best technology which fits to do the job, right? And that is, in a sense, what it is about in polyglot architecture. There is not this one technology anymore, which is kind of the answer to all of the questions you have. You need to have basically the right technology for whatever the requirements are, right? And that is not answered by one technology anymore. You have a lot of different technologies. So if we look at traditional approaches, what happened is that basically the world has used for a long time now the relational database management systems. What this is about entity relationship models. So you have on one side entities and you have relationships, right? And in ER models, basically the logic of your data is materialized, but then you distinguish between a logical and a physical schema. So the logical one is how you think, how things are connected, but the physical then also needs to take into account what your IT is about, right, and how physically this is then implemented. And then you use SQL queries, as we also just heard, right? SQL as the structured query language, as kind of the methodology to then take advantage of the entity relationship models and the data stored there. So the database landscape in the 1990s and before, coming from the 70s, was mainly relational database management systems. Then in the years of 2000, there was a need that companies were doing data warehousing. So a lot of long-running queries were happening there, which had different requirements basically to what then basically was done with the former relational database management systems, which went a little bit back into the operational mode, where it is about short transactions, about querying basically in an online fashion the data, versus data warehouse was more the question of analyzing huge amount of data, right? And then in the year 2010 around, new technologies came up from NoSQL, Hadoop, and these kind of things, which were then also about how can you store documents, as an example, how can you store JSON formats, and so on, right? And then more recently, basically, on top of that, also graph databases, Spark as another alternative, basically are coming up and are getting more and more popular. So why is that, right? If we look into today's IT, this is still the reality you see here, right? Storing the data, right? And I mean, just asking the obvious question, what is the problem with that, right? And the problem is really coming in a lot of different ways. I mean, one of the problems, of course, is the obvious one: who understands that, right? I mean, understanding that is not as easy as it should be, right? Most of the times, you have IT people who may or may not understand it with enough time. But then on the other side, you have business people who really should take advantage of this data and of this data model, right? But how should they, right? I mean, who understands here what the bottom line of that is? Then the question of agility, right? I mean, typically in a enterprise-wide data model, as this could be, right? I mean, of course, in a bigger enterprise, it is a lot more complex than what you just see, right? But if you have defined that at one point in time, how likely is it that you really change it, right? And you have new requirements, you have new demands from your business users. How can you change that, right? It is not really easy. And then you have a need to materialize relationships, which is also something which is not really logical, right? I mean, you have connections in your data, but in a sense, sometimes you need to materialize that before, right? And then, as I mentioned also on the last slide, you need to distinguish between a logical versus a physical data model. So here you have a logical, then if you basically transfer that to a physical data model where you take advantage or where you consider also the hardware, the underlying structure you have basically in your IT, then it's getting even more complicated. And then to find out, hey, where is really my data? Where's this chunk of data I really need for my query becomes complicated at best. And then what happens most of the time is, in order to optimize this data model, to optimize a given query, sometimes you need to do optimizations. In other words, sometimes people are materializing result sets of query and all those kind of things. That is really a problem, right? So typically you're then at a relational crossroad, which means you see something? Good. Which is basically you have to decide which way you want to go, right? On one side, you could say, okay, I want to have a really rich model, right? I want to have the power, and I want to really have the data stored in a way that there are no overlaps, that there are no redundancies. That's one side to see it. But the other side to see it is then also there's a need to denormalize data, right? And if you denormalize then data, you are running into the problem that, of course, your data model gets simpler, right? But you have redundancy, as I just said, right? So, time to do some trivia. What do you think is the most powerful database in the world? I mean, we have seen the report just in the last session, but in the end, that is not really true. The most powerful database in the world is the human brain, right? So here is something I found about life science. They say the human brain's memory could store the entire internet. Whether this is true or not, I think research is still going on. What the capacity of our brain is. But on the other side, if you look at response times as an example, right? I mean, our human brain is, of course, unbeatable, right? Because you do things just in real time, right? I mean, your brain is capable to do that. Question is, how does it do that, right? In the end, we have synapses, and these synapses are part of your education process. When you grow up, they are connected with each other, right? So you have connections between synapses, right? What can we then learn from Mother Nature, right? There's an alternative to this relational database model we have seen before, and the alternative is really a graph data model. And a graph data model is exactly the same as you have seen on the last slide when we talk about synapses and their connections between each other, right? In the end, a graph data model exists basically on the notion of having nodes and connecting these nodes with each other. And you see immediately when I use my hands that is the most natural way for me to explain something, right? I mean, I typically talk about objects and I talk about how are they connected with each other. That's what we do, right, in our gestures. So what are the advantages using a graph database? Mainly it comes down to 3 advantages. So it has operational efficiency, it provides flexibility, and it provides a fast time to market. So how does it do that? It does do that on one side that we don't have this distinction anymore between logical and physical, right? When we talk with customers, to explain their business models, what they typically come up, they go to the whiteboard and they give us basically an understanding on a whiteboard about nodes and their relationship between each other, right? How can you then translate this into a data model? It's super straightforward because that is already the physical data model, right? You already can take that immediately and you can use that as the physical data model in a graph database because that's exactly the representation we as human beings typically talk about. So here is the property graph model we are using in Neo4j. So typically it is about nodes and relationships. Here in this example you see two nodes. So two nodes are persons and one node is car. And these nodes basically they can hold properties, which in relational database are more or less called attributes. So they have a name, they are born on a date, and they might or might not have a Twitter hashtag. That is already what I will come back later on. The thing that it is the schema is not enforced, so you can have different schemas for different nodes. And then you have another node, which is a car in this example, which has a brand name, which has a model name, and so on and so on. And you could have now another, we talk about labels. Labels are basically categories of these nodes, right? So you could now introduce another car, which has another brand name, I don't know, Volkswagen as an example, with a different model, which has completely different attributes. Or a Tesla as an example, which is completely different from a Volvo in this case, right? Because it's an electric car, has a different engine and all these kind of things, right? And now these nodes can be connected, and that's the point of the relationships. So here we have a relationship, Dan is father of Anne. So these relationships are directed. So you see immediately, right, it doesn't work the other way around. So if Dan is father of Anne, then the other way around does not work, but you can still use this relationship. So if you want to find out from N who is his father, you just take the relationship and go from the other direction, right? And then you have here a relationship called lives with. So Anne lives with Dan, and it is relatively straightforward that in this case, of course, this is bidirectional. But you can, but you don't need to, but you can implicitly make this bidirectional by saying, okay, Dan also lives with Anne, right? And then you have other relationships like owns and drives and things like that. And the good thing about the property graph model is that you can instantly basically create new relationships on the fly, right? So you could now have another relationship from a person to the car which says likes or doesn't like anymore for whatever reason, right? You can instantly create that. That is exactly one of the advantages of the property graph model. So you see here then, if you compare basically the relational database model with the graph model, that this relationship is always materialized. So there is no need anymore to have this need, in this case, a person-friend relationship materialized, where you would need to materialize that because it's an end-to-end relationship. You don't need that, right? In graph model, it is always materialized, the relationship. We have implemented on top of the property graph model a query language called Cypher. And you see here in this example how easy and how straightforward it is, right? I mean, you don't need to be an IT person to understand the Cypher query here. So match person name Dan, knows person name N, right? And then give me basically, is that existing, is that not existing? Or if there's a variable, who knows Dan, and all this kind of thing. So this is pretty straightforward and can be understood by basically everybody. And if you compare that now with SQL, I think we had this example even before in the talk. Just ask yourself, find all direct reports and how many people they manage up to 3 levels down. Same like the example was before, find friends of friends of friends, and so on and so on. In SQL, I mean, I'm not saying that this is the only way to do it, but in the end, it's an awful lot of work, right? Because you need to materialize, first of all, your the managers or the employees managing, reporting to him, and with that, you need to have another result set, and so on, right? So it is really complicated work, and also to understand then the SQL query on the right-hand side, is not trivial, let's say it this way, right? And if you compare this now to a Cypher query, you see the advantages and the beauty of the Cypher query, right? Because in this case, it is relatively straightforward. I think people really can understand that immediately. So you have a match, you materialize the relationship between each other, managers. You even specify here how deep you want to traverse the data, and then you have specified basically the name of the manager, and then you get a return result set. Relatively easy. I'm not saying that this is something a business user needs to do, but it can be done, right? Let's say it this way. And the beauty of the Cypher query is even going further. So if you would say on the right-hand side with SQL query, okay, I don't want to see, I want to open it up. It is not only interesting down to 3 levels, I want it 4, 5, 6 levels and so on downwards, right? That would be a major effort on the right-hand side. Versus on the left-hand side, if you see the Cypher query, all you need to do is basically, you don't see it, the manager's 0.3, you would need to specify here a more depth, right? You would say 0.5 as an example, and then you would traverse 5 levels downwards, right? That is all you would need to do, but the Cypher query in itself remains the same. So if you translate this then also into benchmarks, and if you see where the graph databases really give you the competitive edge, you see this example here and this scenario here, right? It's about the connectedness and the size of data. That means, or translates to, the more connections you have within the data, then the more complicated it basically gets. You see the green curve here. The more it is connected, then relational and other NoSQL databases typically have an exponential growth, right? So as an example, if you need to do a join in a relational database model going over 5, 6, 8, 10, 12, whatever tables, that exponentially grows, right? And the more data you have, the worse it gets, right? Versus on the other side, if you see the graph data model, it is straightforward because in the end, the relations are already materialized, means it doesn't really matter if you start, like in the last example, if you start with a specific manager or with a specific employee and you want to find out how many people report to him, her, right? It doesn't really matter if you have 1 billion records in your database or 1 million or more or less, right? Because in the end you start there and you traverse basically the connections down and you can completely ignore all the landscape around that. And that's a major advantage, right? Because in the relational database that doesn't apply that much, right? You typically build result sets based on the size of tables and on the selectivity. So when we derive now the advantages using Neo4j from that, then the operational efficiency, which I showed a couple of slides before, what does this translate to as an advantage? The query speed and the performance for connected data, that gives you, of course, the operational efficiency. Flexibility, as said, right? I mean, it's schema-free, right? That means a node, a label of a car, as an example, can be an electric car, it can be a traditional car with petrol, it can be a gasoline, it can be a bus, it can be whatever, right? So it's schema-free, and you can connect things outside of the traditional thinking of, yes, I want that basically connected based on what I needed to specify in the SQL schema before. We are talking about traversing versus joins, and that's the major advantage, right? I mean, it is, as said, already materialized, and as simply follow the relationships going out, right? And that is, of course, from a speed and from a flexibility standpoint, by far better than materializing that all the times when you need it in SQL. And then time to market. The Cypher query language, as you have seen, is very, very easy and straightforward, and you can adapt it to your needs, and you can easily change that. So now you may ask yourself, what is the native graph database and what is the difference from a native graph database to a general graph database. There are a couple of them around that. So in the end, what a native graph database provides you is that the application thinks in graphs, right? And the application basically generates or can generate in a query language which recognizes this graph and which already connects things, which is Cypher in this example, right? And then the processing engine knows that this is a graph. It traverses rather than using joins, and then stores the storage. The native storage of the graph is also in a graph fashion, means it is already materialized. Why do I say that? I say that because there are other graph databases on the market which are sometimes just based on relational databases, right? Which means you have on one side the advantage of the graph in the application side, but the storage doesn't really play out there. So now let's come to the architectures and ecosystems. Basically what we see is three different patterns in Neo4j architecture. So one is the primary store. So when Neo4j is used as a primary store, basically then Neo4j is used for reads and writes. Sometimes Neo4j is used as secondary stores, where the access is mostly a read access, and the updates will be done in a batch fashion. And then we have operational data stores or master data stores, where it's mostly about reads and scheduled batch updates and integration logic. As one example here, we have a customer who had an identity and access management problem. They needed to compute a resource authorization in real time. So this was about bundles in telecommunication, where you needed to decide on the fly, basically, is somebody allowed to subscribe to this new service, and what are the consequences in pricing and so on and so on. It was taking basically up to 20 minutes for large customers, pre-calculation, caching it, and stale the data. The original architecture was basically based on middleware services, so 42 channels were triggering middleware channels, and there were backend systems, 35 in this case, right? What was done as part of this project was, in the new architecture, the relational database was replaced by a graph database, by Neo4j, and then as a result, you see here that the response times were reduced from seconds to milliseconds. The code maintainability improved, so it is very easy, basically, to see what is going on in the system. It can be improved, it can be changed all the times. You see here the quote from the project manager. He says, "The Neo4j graph database gives us drastically improved performance and a simple language to query our connected data." So as a secondary store use case, Shutl eBay, so this is a service basically for big cities, which provides the ability to deliver goods within an hour, as an example. So what they wanted to do is to come up with quotes for delivery slots. So in the end, they wanted to provide you 20 potential delivery slots, let's say in London, to say, okay, you have ordered this good. It costs you, if I deliver that within an hour, it costs you, let's say, £20. If you get it within 2 hours, it's £5. If you get it within a day, it's, I don't know, whatever on top, right? It took them 2 seconds to come up with a single quote for a delivery slot, and that was, of course, not acceptable, right? Because you want to provide this information, of course, in a real-time fashion. So the original architecture was a monolith based on Rails. So what the solution basically provided then, or what we've done, is to break the application up into services, different services for quoting, for booking, for feedback. And the key goal was to improve the speed of quoting a Neo4j backend as this service. So here you see basically the new architecture. So on the left-hand side, you see different services, one service for booking, one for quoting, one for service. And on the right-hand side, you see that the data from a relational database was basically in nightly batch jobs populated, right? And in the middle, Neo4j as the graph database was used to take advantage of it. Did it work? Yes, it did, right? I mean, here is the senior developer of Volker Pacher. His quote was, of eBay, Volker Pacher is his name, "We found Neo4j to be literally thousands of times faster than our prior MySQL solution, with queries that require 10 to 100 times less code." So that is a major achievement. And he says, with Neo4j, we can provide functionality that was previously impossible. A couple of other examples using Neo4j as a data source, also as a secondary data store. One of it is basically the largest parcel service based in Germany. So what they do is basically using Neo4j to calculate the routes from the sender to the receiver through all the delivery centers and And the magic here is that, of course, you don't want to overload trucks, right? If a truck is full, then a truck is full. And you also want to guarantee that the truck driver is able to get rid of all his parcels within his business day, which is 8 hours. We also see use cases for recommendation engines and fraud detection. Just a couple of examples. I mean, here would be a sample architecture for fraud detection. So our operational system can feed basically incoming events into Neo4j, and then an application would basically detect if fraud or if there's likely that fraud has happened. What you could do then with this data is, okay, you see that there's, as an example, a skimming of your credit card has happened, right? You could use data integration. So we have done that in a demo using data integration and take basically internal data from a relational database management, let's say a CRM system, as well as external data about credit risk, about the location and all these kind of things. Provide this basically in a management console to a fraud analyst, right? And then you can also generate machine-to-machine actions by saying, okay, I want to cancel the credit card, I want to cancel the transaction, and so on. And that is not the entire truth. I mean, what you can do on top of that is then also, of course, to propagate this data back into the CRM system and back to Neo4j to close the loop and take advantage of the full data. If we take a sample architecture for a retail recommendation, so what you can do is basically beside on the left-hand side, this will not go away, right? I mean, you have an operational system, an internet shop for delivering goods, for invoicing, for shipping, and so on and so on. But if you see the right-hand side of the slide, you see that recommendations can be provided using Neo4j, probably also enriched with external data. What is meant there, right? I mean, you take advantage of the connections within your data. You take advantage of connections within the articles, as an example, to say, okay, these are similar articles, these are complementary articles, but then also enrich this with external data. So what, as an example, what you could do is basically say, okay, as an external data, there are events or the weather forecast or whatever is happening, and then also this has an influence in recommendation. I mean, just take as an example, if there is an earthquake happening like a couple of days ago in New Zealand, you could then, as a recommendation, also recommend books about earthquakes, right? What is happening there and things like that, right? With that, you need to react on real-time events, right? It doesn't happen anymore, or it doesn't help anymore if you pre-compute all these results a couple of days in advance. So ODS, MDS use cases, what we see a lot is basically in operational data stores, there is an additional operation on the integrated data. Means it gives you the opportunity to do more with it, to have more ways to analyze your data. And in master data systems, what you want to do is provide reference data to other operational systems. As just one example here, we see in insurances a common scenario where an insurance company, basically they have that data layer, and it's unlikely that this will be replaced, right? Sometimes this is on mainframes. There's a lot of logic in it, insurance logic, mathematics, and things like that. So it's unlikely that this will change, right? But the demand really changes, right? So previously, this was about in-batch load the data into these data layers, into these mainframe systems. And then you had basically a 9-to-5 access pattern to this, right? But what happens now is basically that with the usage of the internet 24/7, you cannot provide this anymore, right? If you have batch updates, right? Because then essentially the system is closed and you cannot provide access to the internet anymore, right? So what you can do then, and what we have done with customers, is basically provide an MDM layer, which is able basically to provide the service which has redundant data, but also data to the underlying system. So you don't need to store everything there in this MDM layer, but you need to store what is available basically in the data layer beyond. So IoT touchpoints, just briefly, I mean, there are multiple ways how a graph database, namely Neo4j, can help you in Internet of Things. It's about security access management. It's about managing the devices, billions of devices. What is if there's a patch update? You have millions of devices out there. There's a patch update. How do you know what is affected, right, and in which manner, right, and what the implications are to the infrastructure? Then an MDM layer, as just said, basically just providing you the knowledge of all the backend databases. And then if you have complex data models about bundles, about revenue sharing, and so on, this is all a good example of connected data, and this is a good example where Neo4j can help you. To conclude this talk, I mean, polyglot architectures are required to satisfy the needs existing and coming. Again, polyglot architectures is about using the best tool for the right job, right? And Neo4j as a native graph database provides a competitive edge. It provides you agility, flexibility, operational efficiency, and time to market, right? And this is basically giving you the competitive edge to react to these requirements of this time. With that, I thank you for your attention. I wish you a wonderful day and 2 more days on big data. And if you have any need for discussion, I think we can meet at the booth outside. Neo4j has a booth outside. So come and ask us, and we are happy to talk with you. Thank you very much.